Hi everyone. So today we're going to be talking about something called linear approximation. So we'll start off with an example, but just to kind of give you a big picture idea about, what is linear approximation about. Basically, the general idea is that instead of plugging a number into a function that maybe is complicated to evaluate, if you appropriately choose a tangent line to your function, you can get a really good approximation by plugging a number instead of into your original function into the tangent line equation instead. Because generally it's easier to plug a number into a linear equation than it is to plug it into, say, a square root equation or a trig equation or a logarithmic equation or something like that. So because when you're writing the equation of a tangent line, it's always a linear function, regardless of what the original function is you started with, it kind of gives you this universal way to approximate values by plugging them into this linear function instead. Okay, so let's start off with an example. So let's say that you were asked to, maybe let's say you're on a desert island and you're totally deserted. You're trying to engineer a boat or something, a raft to get off the island. And for some reason, you need to be able to approximate to a pretty good degree the square root of 4.05. And you don't have a calculator with you, and you don't have your phone. You just have a pen and paper. So square roots are not the easiest thing to approximate, right? Like you might be able to try to estimate a number. So, right, you might say, okay, it's a little bit more than 2, right? Because the square root of 4 is 2. So maybe you guess 2 point something and you try and you square that number over and over. You could probably eventually find an answer that seems okay. But there's another way to do it. So let me just show you a picture on Desmos, first of all. So here's the function f of x is equal to square root of x. So plugging in the number 4.05 into this function is one way that, if you did have a calculator or if you had Desmos, you could find out the value, right? So if this function is f of x is equal to square root of x, and you're trying to find square root of 4.05, you could do f of 4.05, plug it into this graph. It looks like it's, where is it? I can't get it. Okay, well, I can't get my mouse to sit on it, but I'll tell you later what the value is of the square root of 4.05. But just want you to visually kind of realize that, how can you evaluate a certain number? Well, if there's a function that kind of fits with what you're trying to evaluate, so in this case, the square root function, you can plug that number into the function. So now I'm going to show you the tangent line at x is equal to 4. So why did I choose that x is equal to 4? Well, because that's kind of a nice, clean number that it's easy to find the tangent line at, right? We wouldn't want to try to find the tangent line at 4.05 because that would be a lot of work, but it's not too bad to find the tangent line at x is equal to 4. And if you notice, if we're trying to plug in a number like 4.05, the line, so the black is the original function and the green is the tangent line, you almost can't tell them apart. I have to zoom in really, really far. I've lost track of even where we are, and they still look the same. Right over here, maybe you can start to distinguish them. But my point is that if you're trying to plug in a number that is close to where the tangent line is, you're going to get a really, really similar result by plugging that number not into the original function, but into the tangent line instead. Because the tangent line it kind of sits so close to the original function that you're going to get a really good estimate. If you were trying to plug in something like, let's say close to 8, well, then that wouldn't be so good of an estimate anymore, right? Because those are far apart. But as long as the number that you're trying to estimate is close to the place where the tangent line is drawn, the original function and the tangent line are going to be so close together that they're almost indistinguishable. So I want to kind of summarize that, and then we'll find the tangent line and kind of see how this actually works. So instead of plugging x is equal to 4.05 into the function f of x is equal to square root of x, because that's kind of one way to think about taking the square root of 4.05, we can get an approximation of square root of 4.05 by plugging x is equal to 4.05 into the equation of the line tangent to f of x is equal to square root of x at x is equal to 4. So again, why x is equal to 4? This is basically the closest nice number to 4.05. So that's why we would choose to draw the tangent line at 4. Again, if we did the tangent line somewhere else that was further away, it wouldn't make a good approximation. So we want to make sure that we're choosing to make the tangent line close to the number that we're trying to plug into the original function. So here's the picture that I had up on Desmos, just kind of for reference for your notes. So let's actually find the equation of the tangent line. So how do we do that? Well, we need to find the derivative in order to find the slope of the tangent line and go through that. So we're going to find the equation of the tangent line. So if our original function is f of x is equal to square root of x, well, that means that the derivative is going to be 1 over 2 square root of x. So that comes from x to the 1/2 x to the negative 1/2. That gives us the derivative equal to 1 over 2 root x. And so we want to plug in 4, right, if we're trying to find the tangent line at x is equal to 4. And so that gives us 1 over 2 root 4, which is 1 over 2 times 2, which is 1/4. And so that tells us that the slope of the tangent line is 1/4. And so now we can put it into point slope form and then translate that into, we're going to want to, in this case, write it in for sure, like mx plus b form. So if we write this in point slope form to start, we have y minus 2, right? Because the point that we're focusing on here is the point 4, 2. So y minus 2 is equal to 1/4 times x minus 4. And so this gives us y minus 2 is equal to 1/4 x minus 1. And so altogether we get y is equal to 1/4 x. And then we add 2 to both sides, and it gives us plus 1. And that lines up with what we see here, right? We see that the y-intercept of that line is indeed 1. So when we're doing these types of problems, we're often going to, instead of writing the tangent line as y is equal to, we're going to write L of x. So just kind of rewriting it in function notation. And the reason we're using the letter L is for linear approximation. So our linear approximation equation here is 1/4 x plus 1. So what are we going to do now? So now we're going to, so instead of evaluating f of 4.05, so f of 4.05 would mean plugging it into our original function. We will evaluate L of 4.05. So that would be putting 4.05 in for x in the equation that I boxed there. So that would give us 1/4 times 4.05 plus 1. And so, you might in this case actually type this into a calculator, but at least theoretically, this is an easier thing to compute with pencil and paper. So why is this easier? Well, you can do division, right, by like long division in a way that there really isn't an algorithm for taking square roots. So I'm not going to go through doing this by hand, and you're welcome on the homework to actually type this into a calculator, but just know that like theoretically, you could do this with pencil and paper in a way that you can't with square roots. So if you actually evaluate this, you'll get 0.0125. And so what does that tell us? That tells us that the square root of 4.05 is approximately equal to 2.0125. So by the way, what is the real value of this function? So if you type into a calculator, now that you're back on you're away from your desert island and you can actually type it into a calculator. So the actual value of square root of 4.05 is equal to 2.01246. So that's pretty close, right? Like that rounds up to what we got in our approximation. And so just to kind of show you that on the graph, so the function in black is our original function, and on the graph right now is the actual point at 4.05. So it's 4.05 and then f of 4.05. Here's the tangent line. And then in green is going to show up the point on the tangent line. And so they almost look like there's the same point. I'm going to keep zooming in until you can actually tell that they're two different points, and it's going to take a while. So here we go. So now when we zoom all the way in, that like we've zoomed in a lot. Now we can see, okay, the point on the original function, and I know it says it's rounding it on Desmos, so it actually should be 0.246. It's just rounding it on Desmos. And then this is the point on the tangent line. So they're not the same point, but they're just so close together because of the fact that the tangent line just hugs along the graph. Okay, so this is the general idea of linear approximation. So I want to kind of summarize this as like some general information, and then we'll do a few other examples. So in general, if f of x is a function, then we'll use this L of x. So then the tangent line at a certain value x is equal to a is called L of x, the linear approximation of f of x at x is equal to a. Because the tangent line is different depending on what point you're doing it at, right? So this is just saying that if you draw a tangent line or find a tangent line at a particular value of x, so in the last example we did, we were at x is equal to 4, then that would be the linear approximation of your original function at x is equal to 4 in the example we just did. So why is this useful? Well, because if x is a number close to, so it really matters that you're plugging in a number that is close to that special number you picked out. So in our last example, 4, so we plugged in 4.05, which is close to 4, then it's always going to be true that your original function is approximately equal to your linear approximation. And so what does that mean? That means that instead of plugging your number into your original function, you can plug it into the linear approximation instead. And by the way, this general idea, not this exact procedure, but this kind of general idea of taking a function and approximating it and using the approximation instead of the actual function is used a lot in computers and calculators and all sorts of things. So for example, for evaluating trig functions, your calculator isn't actually like drawing a right triangle or making a unit circle. Your calculator is using some kind of an approximation. And even with things that your calculator maybe can do from scratch, Oftentimes it's using approximation because it's a much more efficient thing to do. And when it comes to computers and calculating things, efficiency really matters because things add up. So I'm not trying to say that your computer is literally doing exactly what we're doing here, but it's definitely doing things that are at least in this same spirit of not using the original function, but coming up with some kind of a good approximation. Okay, so let's look at a few examples. So next example I want to do is I want to find the linear approximation So we're going to find an equation of a tangent line. That's what you should think when you see linear approximation of f of x is equal to sine of x at x is equal to 0. So basically that just means we're finding, it's a new word for saying we're finding the equation of the tangent line. Once we have that equation, then we're going to approximate sine of 0.1. Okay, so how do you find the tangent line? Again, like in the last example, we want to start by finding the slope. So f prime of x is equal to cosine of x. And if we're trying to find the tangent line at x is equal to 0, we want the slope at 0, so we take cosine of 0. Cosine of 0 is saying, when you're on the unit circle, what is the x coordinate at an angle of 0? Well, the x coordinate is 1, so cosine of 0 is 1. So that tells us that the slope of our tangent line is 1. And then to put together the equation, we need to know what is the y coordinate when x is 0. Well, what is sine of 0? Sine of 0 is just 0, right? Because if you take sine of 0, then you're looking at this y coordinate, which is 0. So sine of 0 is 0, and so that tells us that the point that we're going through in this case is the point 0, 0. So our equation, we can actually jump straight to slope-intercept form because we know the y-intercept is 0 if it goes through 0, 0. And so our equation is just going to be y is equal to 1x, which is just y is equal to x, right? Because the slope is 1, it goes through 0, 0. It's just a line with a slope of 1 going through the origin, which is the line y is equal to x. So writing that in our new fancy linear approximation notation, we say L of x is equal to x. So this is actually a really useful approximation to know because it's very, very simple. So in the last example we did, like I said, theoretically it is easier to plug in 4.05 into this equation than it is to take the square root, but it's still kind of, you have to remember how to divide decimals, which I'm sure not everyone loves doing. But this is a really, really easy equation to plug into, right? Because if the equation is just L of x is equal to x, that means whatever number you're plugging in, the output is just that same number. So this is kind of an important approximation to know. I think it's used a lot in if you take a physics class or something like that. There's a lot of places where it becomes important to know approximate values. And so an important thing to know is that basically, when x is close to 0, sine of x is approximately equal to just x, right? Because that's what our tangent line equation is saying. It's just, you just literally you plug in 0.1 and your answer is 0.1. So sine of x is going to be very, very close to actually just whatever that angle is that you're plugging in. So I'll kind of highlight that here because that's just kind of a nifty fact to know. Okay, so let's actually do this approximation. So to approximate f of 0.1, so that would be sine of 0.1, we, instead of evaluating that, we do L of 0.1. And so what is L of 0.1? Well, like we just said, it's just 0.1, right? Because of what how that function works. It's just L of x is equal to x. And so what does this tell us? This tells us that sine of 0.1 is approximately equal to just 0.1. So let's look at a Desmos again to just kind of reinforce this idea. Oh, I'm gonna have to zoom out like a ton. Still have to zoom out a ton. Okay, so that was our last example. Let me pull up this example. So here we have the graph of sine of x. And so here is our tangent line. So our tangent line at 0, as we saw, it's just a line with a slope of 1 going through the origin. So if we were trying to find sine of 0.1, that would be that black dot. That's actually plugging 0.1 into the original sine graph. Trying to plug that point instead into the line gives you this point, which again, we're going to have to zoom in quite a bit to see that these are actually different. So again, the black dot is the actual value and the green dot is the tangent line. So they're really, really close. And so actually, if you were to type sine of 0.1 into a calculator and get a better approximation, so the actual value, and I guess I shouldn't say actual value because what I'm going to write down is still an approximation, but it's at least a slightly better approximation. So the better approximation that exists would be 0.998. I'll put another approximate. But so it's not, our approximation isn't quite as good as the approximation your calculator can give you, but it's pretty close, right? Like it's definitely a decent approximation. Okay, so we're going to do a couple more examples, and actually I think just one more example, and I'll put the next one on the worksheet. So this next example is going to be a little bit trickier because I'm not going to tell you from the get-go what our function is and where we're doing the tangent line. We're going to have to kind of figure that out. So in this example, we want to figure out a way to use linear approximation to approximate 1 divided by 4.02. So basically what we need to figure out is we need to figure out what's our function, right? There's no f of x in this problem, so we need to figure out what's the function that we're using to make our tangent line. And then we also need to figure out where are we putting this tangent line. And then once we have those two things, then it will just be like the previous questions. So first part is, what is our function f of x? So to answer that question, basically we want to think of, what would be a function that you could plug 4.02 into in order to, and get 1 over 4.02. So if our function was, and I would recommend pausing and trying to think about this yourself, but I'll spoil it in a moment. So if our function is 1 over x, well then if we were to plug in 4.02, we would get 1 over 4.02. So that's how we can kind of make this thing we're trying to approximate fit with what we were doing earlier, right? We always want to be able to write down f of something as what it is that we're trying to approximate. So you're just generally for this step kind of looking at what type of function, what are you doing in this function? Are you taking sine of something? Are you square rooting it? Are you doing 1 divided by it? Are you taking ln? Like what is the process that's happening in this example? And then the next thing we have to figure out is, what is a? So what do I mean when I say a? I mean the place where we're going to do the tangent line. So when you're answering this part of the question, you have to figure out what's like the nicest kind of convenient number close to the number that we're trying to approximate. So we're trying to approximate f of 4.02. So what's a nice number close to that? 4, right? So if we do a is equal to 4, is the closest nice number to x is equal to 4.02. So we're just kind of thinking of a nice number close to that number. So once we have these things, now we can just proceed exactly like we did in the last one. So now what we're trying to do is we're trying to find the linear approximation of f of x is equal to 1 over x at x is equal to 4. So that just means finding the equation of the tangent line. So first we find our slope. So the derivative of 1 over x, so that's x to the negative 1. So the derivative is going to be negative x to the negative 2, which is negative 1 over x squared. And then we want to plug in, we want to figure out what that is when we're at x is equal to 4. So we can plug 4 in. So that gives us negative 1/16. And then what point does this go through? So it goes through the point where x is equal to 4. And then how do we find the y coordinate? We plug it into our original function. So 4 1/4. So now we can go ahead and write our equation. So we have y minus 1/4 is equal to negative 1/16 x minus 4. So the fractions are actually going to come out a little bit nicer than you might expect. So we have y minus 1/4 is equal to, so what do you get when you distribute this 1/16 in? Well, when you multiply negative 1/16 with negative 4, that gives you positive 4/16, which is the same thing as 1/4. So we'll get negative 1 over 16x plus 1/4. And then we can add this negative 1/4. We can add negative 1/4 to both sides, and that gives us y is equal to negative 1 over 16x plus 1/2. And so our linear approximation is L of x is equal to negative 1/16 x plus 1/2. So the last step is to basically use our linear approximation. So we're going to find L of 4.02 instead of plugging it into our original function. And so I know, again, this, like, I could definitely see you doing this and being like, this is definitely not easier. I could just type, it's way easier to type 1 over 4.02 into my calculator than it is to do all of this business. But again, it's more of like a theoretical thing. You know, it's, even though it's maybe more steps, computationally, it's maybe this, in this example, it's not, but the general principle is that plugging into a linear equation in many cases is computationally simpler. So if you were to figure out what this all is, you get 0.24875. So that's what you'd get if you were to actually calculate this. And so what is the actual value? So this tells us that 1 over 4.02 is approximately equal to 0.24875. And so what's the actual value? It's 0.24876. So we're like 0.00001 away. So let me just show you one more time on Desmos. And again, I'm going to have to zoom out a ton before we can get there. Okay, so here is our last example. So this function we're looking at 1 over x. And so here's the tangent line at x is equal to 4. So here's the actual value on the original graph. And then here is the point on the tangent line. So again, they look like they're the same point. Oops. And you really, really have to zoom in to see that they're actually different from each other. So that's it for today. So the worksheet will have a few examples that are kind of along these lines, and especially I think what I think is really good practice is doing ones like the one we just did, where you have to figure out yourself, what is the function what is the point where I'm drawing the tangent line and then finishing off the problem. All right, so I will see you in the next video.